For my math IA, I chose to relate my topic to code breaking, which from there I developed the question, how long would it take to be able to correctly guess a password, and how much safer does a password get by adding symbols and or numbers. I chose this research question because we live in the technology age where many people use the internet for banking and shopping. They do not want the information they enter to be available to unauthorized people, so such information is encrypted on secure websites. I thought that this would be a good topic because cracking a password is a process of recovering passwords from data that have been stored in or transmitted by a computer system, requiring several types of math to crack it. This topic involves logarithms, exponents, integers, statistics, and algebra. This topic concerns me because I have to use passwords for a lot of things, and I want to learn how to have a safer and more secure password. This is personally interesting to me because this plays such a big role in everyone's life. My aim is to find the optimal password combining that provides security and determine what are the strongest and weakest passwords. For every password, there are different requirements, including length. Using the equation t equals a to the power of n, we can find t standing for possibilities, a standing for possible characters, and n standing for the number of characters. An example is a 6-character password requiring it be only lowercase letters. With 26 letters in the alphabet, each character has 26 possible values it could be, and with there being 6 characters in the password, you are left with 26 to the power of 6 equaling 308,915,776 possibilities, with a 12-character password including an upper and lowercase letters, 10 digits, and 33 special characters giving 95 possibilities for each of the 12 characters, making the probability 95 to the power of 12 equaling 5.40 times 10 to the power of 23. Considering the time it would take to crack a password, the equations d equals t divided by 10 to the power of 9 times 3,600, or d equals a to the power of n divided by 10 to the power of 9 times 3,600 can be used to solve for d, standing for the number of hours spent trying every permutation of characters one by one. The denominator is the billions of tests run times the seconds in an hour. Based on the computing power of a computer running billions of tests per second, you can pause the video to answer the question below. An example is when using a 12-character password with 26 possible characters, all being lowercase letters. It will need d equals 26 to the power of 12 divided by 10 to the power of 9 times 3,600 equals 2.65 times 10 to the power of 4 hours, or 1,104 days. The table in the next slide shows how the time varies based on the length and the possible characters of the password. As the length and the possible number of characters increase, so does the time it takes in order to crack the password. Using the table, we can see the more characters and variation in characters make the password more secure and requires a cracker more time to crack it. Looking at a 4-digit PIN, it can be cracked in 0.0000017 of a second. Apple charges the iPhone passcode for a 4-digit code to a 6-digit code. This is still only a small fraction of a second, which is probably why they went to the fingerprint and face recognition. Password entropy is a measurement of how unpredictable a password is. Password entropy is based on the character set used, which is extendable by using lowercase, uppercase, numbers, and symbols, as well as password length. The equation E equals log base of 2 times a to the power of n, or E equals n times log base of 2a, is used to solve for the password entropy E, measured in bytes, the smallest unit of measurement in a computer, 0 or 1. Using log rules, the equation can be changed to log base 2 times a to the power of n to n times log base of 2a. The logarithm has a base of 2 because it is binary and has two values of 0 and 1. An example is when using an 8-character password with 26 possible characters, all being lowercase. It will be E equals 8 log base 2 26 equals 3.76 times 10 to the power of 1 bytes. The table on the next slide shows how the unpredictability varies based on the length and possible characters of the password, making the password harder to crack. As both the length and the number of possible characters increase, so does the password's complexity, making the password take longer to solve. Using this table, we can see that the length and the possible number of characters the password may have increased, and unpredictably by increasing the byte size of the password, making it take longer to crack a password. Hashing is a form that can map data for an arbitrary size to data of the fixed size. SHA1, SHA2, SHA224, SHA256, SHA384, and SHA512 are hashing algorithms that use various byte-wise operations on any number of bytes to produce a fixed-sized hash. Because passwords are so vulnerable, a better way to store the password is by using a hash function. The one-way hash function, also known as a message digest, fingerprint, or composition function, is a mathematical function which takes a variable length input string and converts it into a fixed length binary sequence. A good hash function also makes it hard to find two strings that would produce the same hash value. It is possible to deduce from f from hf. Hash functions are said to be one way. Getting from f to hf is easy. However, getting from hf to f is practically impossible. In addition, the hash functions used have the characteristic that even if it is possible for the two data inputs, f and the inverse of f, to have the same fingerprint known as collision, in practice for a given f, it is also possible to find an inverse of f with the fingerprint identical to f. Salting is random data that is used as an additional input to a one-way function that hashes data. A password or passphrase Salts are used to safeguard passwords and storage. Salting makes a password more complex, harder for a hacker to figure it out and defend against a pre-computed hash attack. Different salt values will create completely different hash values. Even when a plain text passwords are exactly the same. Dictionary attackers are magnificated in a degree as an attacker cannot practically pre-compute the hashes. However, salting cannot protect a common or easy guess passwords. Think about a password that could range from the length of 1 character to 6 characters, which had the requirements of having uppercase, lowercase, and digits giving 62 possible characters for each character position that are unsalted. The equation P equals 6 sum k equals 1, 62 to the power k equals 62 to the power of 1 plus 62 to the power of 2 plus 62 to the power of 3 plus 62 to the power of 4 plus 62 to the power of 5 plus 62 to the power of 6 equals 57,731,386,986 shows the possible passwords in order to store all possible passwords that it could be. The equation S equals 6 sum k equals 1k times 62k to the power k equals 1 times 62 to the power of 1 plus 2 times 62 to the power of 2 plus 3 times 62 to the power of 3 plus 4 times 62 to the power of 4 plus 5 times 62 to the power of 5 plus 6 times 62 to the power of 6 equals 345,441,905,742 is used to find the required storage need of bytes. To store every possible hash it could be, we need SHA-256 hashes, which is 32 bytes long. The equation H equals 32 times 57,731,386,906 equals 1,847,404,383,552 is used to find the required bytes of every possible hash. In order to find the total required bytes needed to store the data, the equation D equals 345,441,905,742 plus 1,847,404,383,555 equals 2,192,846,289,294 is used.